Okay. So on behalf of Tamil Nadu Science Forum, next to the warm welcome to you all. This is going to be 55th lecture, popular science lecture for us. Again, we are going with the mathematics topic. Of course, it's tied up with physics. It's purely going to be a mathematics. It's going to be delivered by Dr. Arul Lakshminayayanan from IIT Madras. He's going to be the speaker will be introduced by Dr. Sudoku. So Tamil Nadu Science Forum is a voluntary organization. It was started in 1980 by a few professionals, scientists, and science enthusiasts. So we have been working on the conducting the hall meeting for the initial first year. Later, it was extended to other districts also. We involved in various other activities before the literacy movement. So it became a big movement. Literacy movement is extended to the entire Tamil Nadu. We are working on the practicals. The science popularization is one of the major activities. So the PSL is coming under the science popularization. Apart from that, we are publishing magazines, 2 magazines, one in Tamil and another in English. Entanglement in Sudoku. The Sudoku has been published for the last 30 years, more than 30 years. It is without any advertisement that is continuing. And we have science publications. We have a working group for environment and development. We have encouraging the women scientists as well. We some another group called SAMA. So there are multiple ways that we are doing work in different areas. This is coming under the science popularization. So with that, let me
Thank you. It's my happy duty to introduce Dr. Arul Lakshminayayanan. This talk is going to be at the interface of maths and physics. It's a mathematical problem which is quantized and dealt with. I hope he will tell us also during the talk how he got into this thing, being a physicist. So to briefly introduce Dr. Arul Lakshminayayanan, he's a professor in the Department of Physics in IIT Madras. He graduated from IIT Madras in mechanical engineering and moved to the State University of New York, Stoney Brook, to pursue his doctoral degree in theoretical physics. There he worked with Prof Nandor L Balazs. After completing his Ph.D. in 1993, he moved to Physical Research Laboratory in Ahmedabad as a postdoctoral fellow, and later he took up the position of scientist. He moved to IIT Madras in 2003. As a theoretical physicist, his research interests are dynamical systems, especially Hamiltonian and quantum chaotic systems, quantum information, especially entanglement, many-body physics, and thermalization, random matrix theory, and its applications. I will leave it to you and the speaker now to take up the rest of the evening. Thank you.
Thank you very much, Dr. Sudoku, for that very nice introduction. Thank you, Dr. Vijay, for this very kind invitation to this very important organization, PNSF, which I'm familiar with for a long time, but not had the opportunity to interact. But it's great to hear about the various activities and be familiar with the Entanglement for many of my friends are also involved in this. So it's a pleasure to be here this evening, and good evening to all of you, colleagues and students from various places. both here and online. I'm going to, in the next 45 minutes, share with you work which started as a puzzle more than 200 years ago. And that is the 36 officers of Euler puzzle. And move on to quantum physics. My collaborators in this are very crucially my PhD student who is finishing his PhD, Ahmedabad from Madras, and Karen Shushkowski, who is at the Hamiltonian University, Krakow, Poland, and the Center for Theoretical Physics, Warsaw, and his former PhD student, they've all graduated and are now postdocs, Arul Lakshminayayanan, who's the Gregorian and Carol's. So, without further ado, let's get into the problem. This is actually a castle which you see, medieval castle, and actually Krakow. And the origins of the problem is really 18th century, and at least according to what is handed down to us, comes from a puzzle discussed in Petersburg, where at that time Euler was there in the Russian court, and in fact the queen of Russia was supposed to have posed this puzzle, but of course these are all puzzles which have been going around at that time in many circles. So it was, I will come to the exact nature of the puzzle. So this is the work, and this was covered in various fora. In fact, Dr. Subhashki wrote a very nice article on this in the Hindu when it appeared. And so I would encourage you to see some of these popular write-ups as well. Now, what is all this thing about? We are familiar with some kind of designs with numbers. We do this all the time. And Sudoku is a very popular puzzle today. In the newspaper every day, a fresh one every morning for us to jog our brains on. What is it? It's, in this case, of a normal Sudoku is a 9 by 9 square in which we fill with numbers from 1 to 9, such that there is no repetition of a number along any row or column. In fact, it's a stricter thing in Sudoku because it's split into these 9 3 by 3 squares. We see, so these 9 3 by 3 squares is plus 3 by 3, next 3 by 3, etc. And there is no, as you know, repetition even within these individual 9 squares. So this is a Sudoku puzzle, and this is a solved Sudoku puzzle. And the kind of problems, the puzzles that we're talking about, is very closely related to this kind of puzzle. Now, what has this got to do with physics? And in fact, it has to do with physics already in the discussion. We have heard mathematics, physics, and so on. They're all, of course, very interconnected. You not separate one from the other. You'll be doing it at your own risk. So, I hope to convey some amount of excitement around this. Because the simplest objects, which are these kind of designs, are called lattice squares. And what are lattice squares? So, in fact, I seem to have, there seems to be this slight problem giving. So when this is trying to pick up, so let me a Latin square, let me just describe a Latin square. A Latin square is an array, in general, a d by d array. In fact, what I had written down was a 3 by 3 array, in which no number is repeating along a row or column, and there are d such numbers in them. Okay, so okay, so here is an example, but actually I wanted something more simpler. So let me actually go back. Okay, maybe I will stick with this. Okay. Yeah. Okay. You can see the first one here, which consists of it's just a 3 by 3 square, unlike a 9 by 9 Sudoku. And there are these numbers 1, 2, and 3, which we are filling this up in, such that you can see that there is no repetition along any row or column. For example, there's 1, 2, 3 in this first row, 1, 2, 3 here. If you take the second column, it's 2, 3, 1, etc. So that is called a Latin square. As you can see, that is the basic thing in a Sudoku puzzle as well. It has to be a Latin square. And here is another example of a Latin square. It's slightly different. The first row is the same, 1, 2, 3. But the second one is different. It's 3, 1, 2 rather than 2, 3, 1. And that's actually interchanging the two columns. But these two are different Latin squares. Okay. Now, let's put them together in the sense that let this third square be something which contains the entries of both these squares, 1, 1. Okay, so that is 1, 1 comes here, 2, 2 here, and so on. So we combine 3 and 1 and we get 3, 1. Now, what we notice about this new 3 by 3 grid, which contains these pairs of numbers 1, 2, and 3, is that it contains all the 9 possible pairs. It does not repeat any of these pairs. For example, 1, 1 appears only once, and 1, 3 will appear somewhere. It's appearing here, and so on. So if this is the case, that you put two Latin squares together, and you get all possible combinations of symbols. If you have a d by d grid, d by d grid to begin with, you have d square symbol. If all of them appear, and they can appear only exactly once, then these two Latin squares are called orthogonal Latin squares for some particular reason. Okay, so that's the definition of an orthogonal Latin square. Here is the same thing but written in some different ways. You don't have to only enter numbers. You can have any symbols, for example, ABC. So you can see that using these 3 alphabets, this is actually a Latin square. In fact, the name Latin, the Latin square is simply originating from the entries being Latin letters. Okay, and you can go from the numbers to alphabets and vice versa. Now, this orthogonal Latin square is also called a Greco-Latin square because one uses the Greek letters and Latin letters together for these pairs. So here you can see an example of an orthogonal Latin square. Again, 3 by 3, as I said. Now you have alpha, beta, gamma, Greek letters, and ABC. And you can see that along any row or column, there is every Greek letter will appear only once, and every Latin letter will appear once. Okay, so you can verify that, and there is therefore all possible combinations from alpha A to gamma C, which will appear in this grid. Another way of writing it is, popular way of writing it is through cards, the rank and the color of the cards, or the so here just the actually here the color doesn't play a role. It's ace, queen, and king is one square, constructs one square, and the diamond, spade, and clover are the 3 symbols for the other square. And you can see that this is an equivalent representation. This may not be very clear, but this can also be converted to numbers. Here you see green, and blue for this. Okay, so this is the simple construction of a Latin square and an orthogonal Latin square. Now, I have just talked about what happens in a 3 by 3 grid. Let's talk about what happens in an arbitrary. Okay. Let me try to see if I can start on a slideshow. I seem to be able to do something. Is there some idea of why I can't start a slideshow on this?
Escape.
It doesn't start from this particular thing, I think, and if I start from the first, I might be in trouble. So anyway, let me then come. Okay, so let's just look at 2 by 2, which is the simplest. 2 is what we can, it's fine. So we'll just look at the 2 by 2, which is even simpler, right? 2 being smaller. In that case, we have only two symbols, 1 and 2, and you can see that this is the lattice square. 1, if I put 1 there, I have to put a 2 there, and below also I have to put a 2 and this 1 is fixed. That's it. And then maybe I can interchange 1 and 2, there's nothing else to be done. So this is the unique other lattice square. And if we put them together, you see that you have 1, 2, 2, 1, 2, 1, and 1, 2. You don't have 1, 1, and 3. Therefore, it is not possible for a 2 by 2 grid or D equals 2 to be having orthogonal lattice squares. Yes, you can have lattice squares like 2, but they cannot be orthogonal. So in fact, in D equals 2, you cannot have orthogonal lattice square. D equals 3, you can. I just displayed that. Here is another way of displaying the same thing, but now in the two squares or the two symbols are colors and chess pieces. Yet another way of representing. So here you have pink, green, and blue, and gray, light gray, and some form of red. Okay, so this is also an orthogonal array. That is, there's no repetition of color along any row or column, no repetition of chess pieces along any row or column, and there are only 3 chess pieces and 3 colors. That's the minimum. 3 by 3 we've already seen. 4 by 4 also it's possible. Here is an example of that. 5 by 5, you can, it's not that hard to again see the 5 unique chess pieces, 5 colors, and no color will repeat along any row, no chess piece will repeat along any row or column. Okay, and 7, I've given an example. Of course, missing is D equals 6. This is another view of the D equals 4 case. I've just written it down in terms of Greco-Latin square or in terms of the cards. Ace, king, queen, and jack. No repetition, row or column. Spade, hearts, diamond, and flop. That completes the card in Anglo-Beyond. Now, we just talked about 2 Latin squares and they being orthogonal to each other. We call them, let's say, mutually orthogonal to each other. You can extend this notion and you can talk about, let's say, okay, can we have 3 squares that are mutually orthogonal? Yes, in the case of D is 4, you can have 3 that are mutually orthogonal to each other. Thanks. Let's hope that works. So thank you. And we can have more number of Latin squares are all mutually orthogonal in the sense that if you put them all together, there should be no repetition along any row or column. So here is an example that D is 4. There are 3 mutually orthogonal things. So here you have Greek, Latin, and Hebrew characters, and then there are 4 of each of these in each of these languages, and there is no repetition along any row or column. This is also possible. You can go to just 0, 1, 2, and 3, and that is an example of mutually orthogonal Latin square. 3 mutually orthogonal Latin squares in D equals 4, where D is the dimensionality of your grid. And this is well known that the maximum number of mutually orthogonal Latin squares you can have of D by D size is D minus 1. So, for example, if D is 2, you can have only 1. D equals 1. So actually, you can't have mutually orthogonal Latin squares at all. And you can have for example, D equals 6. You are allowed to have 5 Latin squares that are mutually orthogonal to each other. Okay. So D equals 2, there's only 1, so there's no case of having being mutually orthogonal at all. So so D equals 2 is uninteresting, and for us it's very simple to see that it does not exist. And this is a maximal set for D is 4. But this is not as important. We're not going to go into mutually orthogonal. We're just going to be interested in pairs of orthogonal Latin squares. And the fact that D equals 6 is a very peculiar problem was posed to Euler. In fact, Euler then proved several things. So let me first read out what Euler himself formulated this problem. He said a very curious question which is exercised for some time. The ingenuity of many people has involved me in the following studies, which seem to open a new field of analysis. In particular, the study of combination. The question revolves around arranging 36 officers to be drawn from 6 different regiments so that they are arranged in a square, so that in each line, both horizontal and vertical, there are 6 officers of different ranks and different regiments. Okay, so you want to arrange these 36 officers in a 6 by 6 grid such that along any row or column, you have an officer belonging to a unique rank, to say general, and a unique regiment. And I believe that you may wonder why this is a desirable thing. But suppose there is an inspection of this 36 officers, and the person inspecting it, the king is walking along any row, he gets to sample at least 1 of each rank and 1 from each regiment. So it's actually a sampling problem, and it turned out much later in the 20th century that this was heavily used in statistical design and in fact a lot of mathematical work in this was done by Indians, that I will show later on. But what Euler showed as early as 1779 is that orthogonal Latin squares exist for all dimensions or odd dimensions. D is odd, like 3, 5, and so on. He also proved the slightly more harder case that it exists for all multiples of 4. And then Euler conjectured, since 6 proved really impossible, the number of combinations was enormous, and you should imagine those days without computers and so on. He conjectured that it does not exist for 6, 10, 14, etc. That is, for all numbers of the form 2 plus 4k, 4n. So 2, of course, it doesn't exist, 6, 10, and so on. So this is the Euler conjecture, 1779. And a long time went by, till 1900, Ganstern actually proved, Euler did not prove, but actually he proved that Euler's does not exist in D equals 6. There is still some issues with, I think, the conversion from into PPT. So there were several proofs offered for the Euler conjecture that orthogonal Latin squares do not exist in all these dimensions till 1959, and they were all wrong. Yeah, there seems to be still a problem because of the. So in 1950, two Indian mathematicians, R.C. Bose and S.S. Shrikande, showed that OLS exists in D equals 22. D equals 22 is not appearing in this one, either here or there. Okay. So, but 22 is of the form, 2 plus 4n, and therefore this was quite a shock to the mathematical community. And here you can see Shrikande and R.C. Bose, who then later on partnered with E.T. Parker, and Parker showed that it then exists and actually D equals 10, which is the smallest case after 6. And then together they showed that actually it exists in all dimensions D except 2 and 6. So it's very peculiar that 2 and 6, these orthogonal Latin squares do not exist, but they exist in all the other dimensions. There is a very beautiful article in the Wire on Sharat Chandra Shrikande. In fact, he passed away shortly after this interview in 2017. So here is an 1959 issue of Scientific American, whose cover is a 10 by 10 orthogonal Latin square. You see, this is an orthogonal Latin square in which you have 10 colors, but now you have the colors in, the color in the outer box, the color in the inner. That is the truth. So they will not repeat along any of the rows of them. It's possible to do this, and this is an example of something which Euler conjecture does not exist. It was found in that. And here is this wonderful site for those of you who don't know, the online encyclopedia of integer sequences, those who are interested in integers. They enumerate the number of pairs of orthogonal Latin squares of order n. N is the same as what I've been calling this D, as the dimension of the squares. This sequence reads 1 for D is 1. That's just 1, of course, that's a trivial case. D equals 2, there is none, that is 0. D equals 3, there are 36 pairs of orthogonal Latin squares. D equals 4, there is 3,456. D equals 5, an enormous number, not to be out. D equals 6, 0. 7, even more enormous, 8. And these numbers are growing enormously, and actually they are not known beyond this. You can see this another number here. So beyond 9, these numbers are not known exactly how they are growing. So there is an enormous number of things, not the 0, but actually it is not known in cases like 10, which is the case of great interest, where it was shown that it exists. Exactly how many exist remains still an interesting problem. I want to also mention that this has had impacts in the world of literature. Here is a book which was rated as one of the top 100 novels, like the user's manual. And there is an apartment in Paris which is designed after this 10 by 10 grid. And it's a very interesting novel for you to read. So here is, we return back to the problematic case of D is 6. And in terms of the in terms of chess pieces, okay, so I have 6 chess pieces. Just concentrate on this first square here. This is the Latin square, because there are 6 pieces and none of them repeat along any row or column. So this we know, Latin squares exist. It's just that orthogonal Latin squares do not exist in D6. So let us try to construct an orthogonal Latin square out of this. We know that it doesn't exist, but let's see how far we can go. So what we will do is we will color each of these pieces differently. So, for example, the king here now becomes the green king. So each of the king is now colored differently in each of these rows, and otherwise the rank of the king remains the same as you can see here. Okay. Now the thing is not to repeat the pieces that have already been done here. We should not repeat the colors. Okay. Can we do that? There are now 6 colors. Okay. We seem to have done everywhere except these central 4 pieces. Now, what is remaining are these pieces here. We have to put this horse, bishop, rook, and pawn here. And there are 2 colors, green, that is this color green, and the color cyan, which is missing here. Okay. So now you can try to color the horse here, let's say green. Then the rook will be colored. The rook will be colored here cyan, and you will find that there will be a repetition. You will find that there will be a repetition somewhere of a cyan colored rook. So try as you might, you will find that you cannot fill this in. So I will leave that. You should do this. Trust me that you cannot. Right. So, but what it will give you is something which is almost an orthogonal lattice square. These are very useful. You can read about these. In fact, this particular picture is taken from this paper which we have written explaining our original solution, called 9 into 4 equals 6, understanding the quantum solution to Euler's problem. So you can see more of this in that paper. Okay. Fortunately, this is facing quite severe problems. So let me try the problem. So, moving to a PDF file. Hopefully that will be good. Here, at least I can see these and so on. Yeah. So here is, so let's see what is it that really, what is the mathematics which is lying behind orthogonal lattice square. Here I'm given the case of D is 5, okay, an equilateral example. If we take a row and column, there are 5 rows and 5 columns. If we take a particular row and column, then it fixes uniquely the 2 entries. That is quite clear. So it fixes the 2 entries. For example, the 3rd row and 3rd column fixes E and delta, okay, as the entry. Now, so you won't have another row and column with the same entries. Entry 1 and entry 2 cannot be the same because it's an orthogonal lattice square. You have all possible combinations, D square possible combinations unique. Okay, so but then this actually allows, and this is the key point here, that you can specify the row and an entry 1, and then that will uniquely specify the column and entry 2. Not only you can go from row column to entry 1, entry 2, out of these 4 numbers, you can specify any 2 of them and it uniquely fixes the other 2. So for example, if I say 3rd row and entry 1 is C, there will be only one of these 3rd row entries in which the first entry is C, again thanks to the property of orthogonal lattice square. So it will come uniquely to this, and therefore it will fix the column as 1 and entry 2 as down. You see? And there is another possibility, row and entry 2. That will fix uniquely again entry 1 and column. So this is actually the central property of an orthogonal matrix square. We can specify any two of them. So here, for example, here is again I have written this 3 by 3 orthogonal lattice square, and we can now get another orthogonal lattice square out of this by using precisely what I just now said. So let's see how we do that. So we look at this 3 by 3 array, and we say that this is entry 1, 1, 1, 2, 1, 3, etc. Okay, that is the first thing is the row, next is the column. The entry to that is entry 1 and entry 2, which is what is written here. But if we specify row and entry 1, for example, if we specify 2 and 1, that is second row and first entry is 1, then it picks up 1, 2 as this. The second row, first entry is 1, that is 2, 1, it picks up this. And that is the third column, and the second entry is 2. So that's why you put here in 2, 1, 3, 2. Okay. So by this means, we get another orthogonal lattice square of 3 from this. Of course, they may be related, okay? But you get another orthogonal lattice square. And the other way of doing it, you get yet another orthogonal lattice square. In this case, these two happen to be the same. Okay. So, but the important point is from one orthogonal lattice square, you can get uniquely two other orthogonal lattice squares for a bit by just this by the fact that out of these 4 entries, any two of them uniquely determine the other two. Okay, so here I've just given you some examples of this. And therefore, we can actually specify an orthogonal lattice square by permutation matrices. Permutation matrices of size d squared. For example, the d equals 3 case, we can specify an orthogonal lattice square and a permutation matrix 9 by 9 permutation matrix, where the entries of a permutation matrix are either 0 or 1, and there is only 1, 1 in any row or column. This is called a permutation. You all studied permutations and combinations in high school, so we'll see the role of these permutations. So we have now written an orthogonal lattice square. No, this one is it an orthogonal lattice square or not? There is an audience here. What I showed here, this first one, is it an orthogonal lattice square? Clearly not, right? Because this one is here. So what I have written here is simply the address of these squares. This is simply the row and column. Okay, first row, first column, second row, first column, second row, second column. But let's actually write an orthogonal lattice square, one of the which okay, and let's combine these two, address and the entry. Now you have 4 entries into each of these. I've just combined these. Okay, so this is telling you that the 1, 1 entry into the orthogonal lattice square is 1, 1. The 2, 2 entry into the orthogonal lattice square is 3, 1. But now actually I don't need the square at all. This is actually giving you a permutation of the d square symbol 1, 1 to 3, 3 into 1, 1 to 3. It's giving you a permutation, and it's actually just a permutation of these d squares. That's why you now see a permutation matrix arising out of this. So let's put along the rows, the row and column. Okay, that is this row and column address. And this is the entry into the entry 1 and entry 2. Okay. And then we will enter here. So 1, 1, 1, 1, then we will put a 1 there. Everywhere else that is 0, because in the 1, 1, 1, there is nothing else. There is only 1. Everything is 0. 1, 2, there is 2. You can see that here, and there is 2. Okay. So now you get this permutation matrix, which is an object with just 0 and 1, matrix of just 0. So the fact that there is an orthogonal lattice square, and you can get a permutation matrix out of that, tells you that now the property of being an orthogonal lattice square gets mapped into a particular property of the permutation. What is that property? So we need to see, because there are a lot of permutation matrices, not all of them will correspond to orthogonal matrix squares. Out of these 9 factorial permutations, only very few will. And this is coming back to our thing that any two of them specifies the other two. This property is of use, and we'll have 2 other permutation matrices, just as we got 2 other orthogonal matrix squares. You will have 2 other permutation matrices which come out of the single permutation. And if they remain permutations, then the original thing is actually an orthogonal matrix square. So we will have 2 rearrangements of these permutation matrices such that if they remain permutation matrices, then it is the corresponding object is an orthogonal matrix square of the original. So what are these permutations? So here I'm starting with this permutation P9, which I started out with, which actually gave an orthogonal lattice square, came from an orthogonal square. So one of the ways in which we do this is we cut this into, just like a Sudoku thing, into these 9 by 9 blocks of 3 by 3 matrices. We take this block, for example, and you have 9 entries, you make them the first row. Okay, this is called a realignment. So you take a matrix and you make it a row, but it will be a d square dimensional row. So 3 by 3 matrix to 9, 1 into 9. So that is just this thing here. Okay, and similarly, I take the second block and I make this into the second row here. Third block, third row. So this doesn't change at all, so you don't see the difference, but you will notice a difference here. For example, I take this block and make it into a row, and this one here gets put into it. Okay, so this is what is happening if we have row and entry specification rather than row and columns. This is called a realignment. Okay, so in terms of a matrix notation, I alpha are the specifying the row, j beta the column. Then it's like interchanging alpha and j. That's it. So this is called realignment. In terms of this notation, you may think about it as a matrix specification of matrix elements, and this is the realignment of this matrix. So what we require is that if we start with this permutation matrix and do this realignment, it should also be a permutation matrix. There's yet another condition, the third one, and that is related to transpose. You must be familiar with transposes of matrices. This is called a blockwise transpose. So what we do is, again, we have split this like a Sudoku into 3 by 3, 9 of these things, and we take a transpose in each of them. Okay, and then you notice that transpose of this, and this is unchanged. By transpose of this, we'll put the 1 here. So that's what happens. Okay. Now, if you do this and it still remains a permutation matrix, that means there will be no 2 1s in the same column or row. Then you're lucky. What you started out with was actually a orthogonal lattice square, a permutation corresponding to an orthogonal. Okay, so there are 3 operations, which are actually 2 operations which are done on a permutation matrix. A d square dimensional permutation matrix P corresponds to an orthogonal lattice square of size P if both its realignment and partial transpose or this blockwise transpose are also permutation. And now I come to the subject of my talk and the work, that is quantum mechanics. What is that got to do with all of these things which I've been talking? So just to reiterate, there exists no 2 by 2 orthogonal lattice square that corresponds to a permutation of 4 objects. So there exists no 4 by 4 permutation matrix or permutation of 4 objects such that its realignment and partial and blockwise transpose are also permutation. And we know from Terry and Euler that this is also the case for 36 dimensions. That is for 6 by 6 grid. There exists no 36 dimensional permutation matrix such that its realignment and blockwise transpose are also permutation. So this led to the question, are there quantum versions of these orthogonal lattice squares? And in particular, do they exist for d equals 2 and d equals 6? in which case we know that it does not exist in the usual sense. Does this question make sense? It's somewhat like this, just to give you an analogy. If somebody asks you to solve x squared plus 1 equals 0, and you know only real numbers, you would say there is no solution. But of course, you know complex numbers, and you would say that the solution is plus or minus 12 to minus 1 pi. So no real solutions, but complex solutions exist. Similarly, actually there are ways in which we are going from permutation matrices to what are called unitary matrices, and then we can ask whether similar things carry over, and therefore there is a generalization of permutation matrices unitary. What are unitary matrices? They generalize rotation. You're familiar with rotations and orthogonal matrices. Unitary matrices are sort of complex generalizations of just rotation. And they take orthogonal vectors, such as identity vectors, to other orthogonal vectors. And why is this problem interesting from the point of view of physics? Is because it is related to the problem of entanglement. In fact, this year's Nobel Prize was given to pioneers in the study of quantum entanglement. And this particular problem of orthogonal Latin squares yields very highly entangled states, as I will show in a minute. And therefore, this was, one of the stated. There was an award which was given to by this society in Poland. They identified 5 problems, and one of them is to show. The third one is to find solution to the problem of 36 entangled orbitals of the boiler, or show the solution does not exist. So it was considered as an important problem. Now there is let me ask the organizers. Dr. Vijay is my. I think you have had some issues with the slide. I'm sorry about that, but is there time I should be aware of?
Yeah, you can have to go. Yeah, you can go ahead.
How long?
How much time do you need?
15 minutes probably.
That's fine. That's just.
So, because I want to also, considering the audience, I would like to also introduce some quantum mechanics at a very basic sort of pictorial level into science. We will start with the notion of a quantum state itself. A state is, and the simplest state in a quantum system is one which has access to 2 levels or 2 possible states, which we will call, let's say, 0 and 1. Okay, so like here, 0 and 1, like off and on. And if you are familiar with the spin, you can think about up spin and down spin in some particular direction. And then any state of this quantum system can be in a superposition of this. Okay, so it's not just 0 or 1, but any superposition like 0 plus 1. So now you should go to vectors. Okay, so you should now think about the state as a vector itself, and adding vectors to get other vectors which are also physical states. And if you take such a state of a system in which you have only 2 possible outcomes, or 2 possible orthogonal states, 0 and 1 here, and you make a measurement of this, the probability of getting 0 is modulus alpha squared, where the alpha is this complex coefficient sitting there, and probability of getting 1 is modulus beta squared. So this is known as Born's rule. And if you have 2 states like 0 and 1, they are perfectly distinguished. That is, you can make an experiment and distinguish them perfectly if they are orthogonal. Orthogonal quantum states can be perfectly distinguished. Orthogonal meaning their inner product is 0. You're thinking of them as vectors. Just think of them as if you're not familiar with quantum mechanics, just vectors which are like 90 degrees. Okay, it's just a visualization. Don't take it too serious. But suppose, so in fact, these things are called, classically, if you have only two states, like on and off, these are bits. And if you combine them like this, these are known as qubits. Now they are very popular because of quantum computing. So this is a qubit. But what if you have two of them? You have two bits, they are in these four possible states. On, off, on, off, on, off. Right? But if you have two qubits, that is quantum bits, then they can be in all kinds of superpositions, such as this 0, 0 plus 1. In fact, if it is 0, 0 plus 1, 1, it's a very non-classical state, because what can I say is the first qubit state? I can't say it is 0. I can't say it is 1. In fact, such states are called entangled states, and they have very interesting properties, and that's, in fact, I think a few weeks back there was a talk by this negotiation in this very PNSF forum explaining the magic of entanglement. And here is another famous hero in quantum mechanics, the Schrodinger cat, which is also an entangled state. Schrodinger devised this example so that we can understand that the non-classicality of quantum mechanics itself. And he said that, okay, now let that be a cat in a box, and there is a alpha decay, which is a quantum mechanical process. Let's say that if it happens, then it releases some poison and the cat dies. And if it doesn't, the cat is alive. Okay, so let's say that if it is red here, that is this thing is up. Let's say the state here is up, then the cat is living. If the cat is down, then it is dead. So this is in fact like the 0, 0 plus 1, 1 state. Now the state of the atom gets entangled with the state of the cat. Okay, and then this particular state is a highly non-classical state. We don't know whether the cat is alive or dead until we make a measurement. And so, but these things are actual states. They are not some intermediate states in our head. They are very real states. That is in fact the various experiments related to entanglement have actually shown us. And such simple states like this 0, 0 plus 1, 1 are also called as EPR states, that are famous triple, or they call it Bell state after J.S. Bell, who made very important contributions to our understanding of entanglement. And what has come to be known in the last 30 years is that we can use these states for various things. One of the important things is a teleportation protocol, where we are transporting, so to speak, a state from across very distant places. The state of the particle is not transported itself by using entanglement. Okay, so entanglement can be used in practical situations. But now let's come back to what this entanglement has to do with whatever this coldness that I was talking about. A d-square dimensionality, I'm just reiterating what I've already said, going back to this. Okay, so in fact, I wrote down this in here. Now imagine that we have actually a quantum system in which there are 3 levels, not 2. I was talking about 0 and 1 as qubits. So there is, if you go to 3-level atoms, 3-level system, they are called qubits naturally. And let's call these 3 energy levels or states 1, 2, and 3. And let's say that you have 4 of them, okay, 4 such atoms or qubits. Then you can construct a quantum state out of this by a superposition of all of these states here. 4 ones plus 1, 2, 2, 2 plus 1, 3, 3 plus all of them. Such a state is considered to be a highly entangled state. Just like the Bell state was for simply 2 qubits. But suppose you have 4 qubits, how entangled can it be? So this is the question. And the claim is actually out of the orthogonal Latin squares, you can construct highly entangled states. In fact, these are called absolutely maximally entangled states because you can take any four of them, cut it into any two, and they will be maximally entangled. Okay. So there is a notion of how entangled things are, and they are maximally entangled. So you can construct out of this, out of every orthogonal lattice square in D by D, you can corresponds to a four-party state of D level atoms. Okay, so now let us try to see, okay, can we take these orthogonal lattice squares which we have constructed and in some sense quantize them? Here is one attempt. Okay, so let's look at this good old 4x4 orthogonal lattice square. Remember, this is not just a lattice square, it's orthogonal lattice square because there is both number and color. Color does not repeat and number also does not. Now we can do this following very simple thing where we convert each of the entries, which is just a number, to a vector. Okay, so this vector is now written like this. If you don't know the Ket notation, you just think about this as a vector 1. And this is the vector 2. And this is a four-dimensional vector space in which there is these four vectors, but it's not only these four vectors. See, the color is also a vector. So it corresponds actually to two particles in which there are four level atoms. So I would read this 2 here as a atom in which the second level, it is there in the second level, okay, and the color is green. So this is like 4 level. Okay. Now, the fact that these are all different, we should require these vectors to be all orthogonal. How many vectors? Actually, 16 vectors. There are 16 vectors and they should all be orthogonal. So we are actually looking at a 16-dimensional vector space that it will be all orthogonal. But it's not so clear as to what. So this is too simple. This particular thing is classical to quantum, is very simple. Quantum mechanics allows for much. And what is that much more? That much more, for example, is the example in D, where you again have 16 vectors that are orthogonal, but there is actually some property of this which makes it like an orthogonal Latin square. So it's not just that these 16 vectors are orthogonal, you always find that, but they are very special properties of these entries which are very similar to that of orthogonal Latin square. And therefore, the study of quantum orthogonal Latin squares has just begun. You can see this in some other examples again in this paper of ours. So, a quantum orthogonal Latin square is basically a collection of these d squared orthogonal vectors or states, quantum states, psi 1, 1, psi 3, 3 for the case of cuprids, okay, which are orthogonal, but not just that. So there are these orthogonal things here. We still have to take into account these two, this pair property, which I told you in the orthogonal Latin square. Any pair specifies this. That is coming because of this realignment and blockwise transpose, which I told you. So this particular orthogonal set of vectors, psi 1, 1 to psi 3, 3, is specified by one unitary name, which is of dimension 36. Okay. Now, the corresponding quantum orthogonal Latin square will be really a quantum orthogonal Latin square if and only if under these two operations of realignment and blockwise transpose, it remains unitary. Just as in the classical case, it remained unitary, it remained a permutation. Now it has to remain unitary under these two operations. So the search for the quantum solution to the Euler problem boils down to, in this language, finding a unitary matrix in 36 dimensions, which is like a generalization of a rotation in 36 dimensions, such that these under the realignment and clockwise transpose, it still remain a unitary or an orthogonal kind of rotation. And I will not tell you exactly how we did it because it's technical, you can see the papers. But it ultimately comes down to also having very special three orthogonal bases in 36-dimensional space. So here is actually the unitary matrix in 36 dimension. The non-zero entries are written here. Very interestingly, the entries we found had to be complex. They cannot be real. So it's not really an orthogonal matrix. We haven't found that yet. And interestingly, this was determined essentially by one number, which is the golden mean. You must have come across the golden mean or golden ratio before, square root of 5 plus 1, which is coming from Fibonacci number. So on, it's one of those recurring things in science. And remarkably, it appears in this solution. And a 20th root of unity, e to the power of 2 pi I by 20, which is this complex number, comes into play. With just these numbers, we are able to construct such a unitary matrix. And so what exactly is the solution mean? So let's actually go back to this example which I have here. So if I look at this as an orthogonal lattice, the quantum orthogonal lattice square, you see there is no problem in our thinking about the state 1 or state 2 because this is the state 2 is an entry is green and the level is 2. But if I look at this state here, I will have a combination of 3 and 4. But not only that, the color is, you see, blue and green. So this is actually an entangled state in which the color blue and green are there, and the numbers 3 and 4, and they are actually forming a 2-qubit entangled state. Okay, so we cannot separate out here the number and the color because if I have just 3, I can say 3 and blue, or 4, I can say 4 and green. But now I can't say whether it's green or blue. I can't say whether it's 3 or 4. This is so the same way we have to put our officers of Euler who are situated, remember, in Russia, into these kind of superpositions. But these officers, okay, we go from a war thing to cards here. So they are in kind of superposition with this. So I can't put just ace and club and so on. I have to have superposition. Ace and club along with king and heart, king and spade. So this means that at this particular square here is a superposition of these. So this is actually an entangled state where the regimen and the rank, they get entangled. If you allow for that, then you can have actually a solution to the Euler problem in D equals 6. Now I already said that D equals 2, but it's not possible. It's very simple to see. Quantum mechanically, is it possible? D equals 2, I have not answered that, I have not put it in here. Actually, it was known from about 20 years ago that it's not possible. So even if you go to quantum in D equals 2, it's easy to see that it's not possible. To put it in physics terms, in terms of these qubits, if you have 4 qubits, you cannot find an absolutely maximally entangled state. But if you have 4 6-level atoms, you can put it into this absolutely maximally entangled state, and that describes the solution of Euler's problem. To put it in another way, to give some kind of an interpretation, since the number 6 comes up in dice, number 2 comes up in coins, number 6 comes up in dice, there are 6 possibilities. So we can describe our state, which we found as a state of 4 entangled die, such that actually the state is such that if you take any 2 of them, randomly you can just select any 2 of them and measure them, you can find the state of the other. That's how entangled is. Although all possibilities are there. So it looks completely random to you. However, you can take any 2 of them and measure them, and you will know the outcome of the other. So that is the notion of entanglement. Entanglement is it will look as if the outcomes are random, but if you look at it, there is a deeper correlation in that. And that correlation in these 4-particle system is coming out of these solutions. So to summarize, the Euler's classical problem of 36 orbitals is in fact impossible to solve. We haven't solved the impossible. There are no permutation matrices that there is realignment and partial transpose are also permutation. That's a technical statement there. However, there are unitary matrices of size 36 that do have this property, and therefore they give a quantum solution to this problem. This leads to a state of 4 particles where the choice of any 2 of them renders the others in an orthogonal set of 36 entangled states. And I haven't discussed any of the uses and so on, but absolutely maximally entangled states have many uses in quantum error correction, which is important in computing. In what's called parallel teleportation, I alluded to teleportation. In the study of quantum gravity, in the construction of what are called perfect tensors, whatever we constructed is also known as perfect tensors. So we solved some problem with that. There are open problems. We are addressing some of them. How many are actually equivalent? And more than 4 particles type state. And this kind of opens up the field, when Euler started his study, this was one of the first studies, combinatorics. Combinatorics now is a very vast and beautiful subject. We have started in some way, this particular work has contributed in some way to the nascent field of quantum problems. Thank you for your attention.
Question?
What is it mean for when even quantum thing is impossible? Does it mean if you fix in the 2x2 case for 4 qubits thing, if you fix the first 2, the other 2 can be still arbitrary, right? More combinations are possible. Does it mean? What does it mean for that? That there is no maximally entangled, right, 4 qubit states, right? Yeah. So if I fix 1, the other we cannot decide even now. That's why, is that idea? Is that the statement?
Well, actually, there are various ways of looking at it. So one is simply in terms of entanglement. It means that no cutoff with no qubit will be maximally entangled with another 2 qubits. So you cannot make so precisely. So when you make measurements on just 2 of them, any arbitrary 2 of them is important. You cannot decide on the outcome of the.
So you can't decide about what happens in the distant case.
Yeah. So from a mathematical perspective, what we are dealing with will be 4x4 unitary matrices, and we are requiring too much of this when we are asking that there are too many constraints, they are not satisfied. When we are asking that both the realignment and log-wise transpose also be unitary, it is not satisfied. So in fact, the famous C0 gate is the most entangling in this case. So we can go from states to gates and back and forth. Because this unitary operator is only acting on 2 particle states. And when we are talking about states, we are talking about 4 particles. Yeah.
Okay.
Thank you for that presentation. Would Euler agree with your solution? Because most media, the news comes out is that the 324-year problem of Euler has been solved. So really, I see that one of your slides you actually mentioned the Polish National Quantum Information Center actually says, please use quantum computing to figure out if this problem can be approached or not. So the award that was given was for the quantum application of quantum computing in this to this problem rather than solving Euler's problem itself. Is that correct?
Absolutely. You can see the first line in the summary. Euler's classical problem, it's impossible to solve. Nobody is arguing.
So, okay, there's no solution.
There's no solution.
And secondly, since colors are given so much importance in the classification, I was just wondering why the opening slide had Sudek's name in the green color and the rest of the fine.
Because he's from IIT Madras.
Is that the reason?
I think so.
We don't have the
He's more local than the others. The others are more not local. He's entangled, but he's in a different state. But they're very good and perceptive questions. Thank you. I have to be careful about the coloring schemes I use.
So when you decide that a particular problem cannot be solved, is it by checking whether the permutation matrices and the other unitary matrices don't exist or something like that? Or
Yeah, it's a good question. Actually, the case of clearly it was we were working on this problem for about 5 years or so, and we were coming to the conclusion that it does not exist even in the equals 6. And it is much harder to prove that something does not exist than to prove something exists, because if I give one example, it is settled, which is what happened in this case. But to prove that it does not exist is actually a more harder problem. In the case of D equals 2, so in the case of D equals 6, we could not prove that. Of course, now we know that any such proof is incorrect because we found such a thing. But in the case of D equals 2, yes. I mean, as I mentioned, it's a question of satisfying various constraints, and you can see that all those constraints cannot be satisfied in the case of D equals 2. And there are other ways of seeing this. There are many ways subsequently of seeing that this is not possible for D equals 2. But yeah, that's actually more hard.
this is a related question. You mentioned that Shrikande and the other person, see both they proved that the solution exists.
Yes.
But before that, there were many people who had actually shown that it doesn't exist. I mean, incorrectly shown.
Yeah.
But so how did so many people get how did they?
Yeah, I think bright people make mistakes. That's the case. And I mean, it was, I think, well, it was clearly a difficult problem. And in fact, Euler himself did not solve the problem in 6. It was left to actually an amateur mathematician. Yes, in 1900. It involved classification and enumeration, but the important thing is classification. That to see inequivalent classes and to see that it does not exist in those. And there are, by the way, connections to other parts of mathematics, finite geometry, and other things which I'm not. Also, I'm not a mathematician, by the way, despite. So I don't know.
Okay, 2 small questions. You have shown one solution. There could be more solutions in D equals 6.
Yes.
There are possibilities, right?
So, by the way, I did not show this one, I showed 3, because there is U, realignment, and blockwise transfer. And I can share with you for the first time today that actually there are infinity. We have shown that there are infinity.
Yes, the number of solutions. And so even in other cases where solutions exist for orthogonal things, if I extend it to unitary conditions, there will be much more solutions, or even infinite number of solutions.
Absolutely. So the orthogonal Latin squares are just a small set. In fact, there are innumerable set. But there is an uncountable infinity in all dimensions. So we have some constructions of these. So that those are all these quantum orthogonal elements. So in fact, it just It's like going from integers to real.
Is it not countable infinity?
No, it's not.
So throw back to the historical background of this problem. So I was, you showed us the castle in the beginning.
It's just because it looks pretty.
Yeah,
Okay,
but that was not Poland. So I was wondering if the initial Euler statement of the problem had all these derivatives operators as male operators, which did it go given, therefore could this have a sociological distribution?
has to be addressed to all of them. We can't do that now. That's another impossible problem.
Good evening, sir. So you told regarding the applications, so could you throw some light on quantum gravity, how it is used, or what is the process going on?
So very little light on it, but there is these things called tensor networks, which are kind of models of space-time. And in that, there is the kind of nodes which are there in this network are these tensors, but tensors are just generalizations of these kind of unitary matrices which I have talked about. So at each of those nodes, you will have these kind of 36-dimensional matrices or any d-square dimensional matrices or any actually some other dimension of it possible. And then the entanglement properties in of such circuits are somehow also related to the problem of quantum gravity. So in fact, to be a bit provocative, it is said that entanglement is the fabric of space-time and so on. It won't actually, I'm not an expert in this, but it's an interesting viewpoints which are at the moment being.
Thank you, sir.
So it's going to be a formal thanks, and let me offer my first thanks to Dr. Arul. Yes, it was immediately accepted and I made a request. And in fact, I have not been touch with you for the last 3 days, and yesterday I reminded him quickly. They remind that I have committed as I will. So thank you very much, sir. I would like to thank Dr. Govindarajan for arranging this call and helped us to get this IMSC hall. Thank you very much. And I would like to thank Dr. Shubha for introducing the speaker. I thank all the audience for coming. Thank you very much. We have tea has been arranged.